The universe may contain objects that do not die through explosion, collision, or collapse, but by slowly leaking away into nothing. Current models suggest that some black holes could gradually lose mass over unimaginable spans of time, even though gravity is expected to trap everything permanently beyond the event horizon. A black hole begins as one of the most stable gravitational systems known in astrophysics. Matter, radiation, and even light crossing the event horizon are expected to remain trapped inside a region where escape becomes physically impossible. That expectation creates the foundation of the paradox, because evaporation implies that the system is not completely closed after all. The proposed leakage process emerges from quantum behavior near the event horizon rather than from inside the black hole itself. Fluctuations in empty space may allow particle pairs to briefly appear, with one particle escaping while the other falls inward. Over extreme timescales, this imbalance could slowly drain energy from the black hole, producing a measurable loss of mass. If this process is correct, the observable pattern becomes deeply counterintuitive. A black hole would not only consume surrounding matter, but also slowly diminish in size through its own radiation output. The contradiction appears immediately because an object defined by permanent gravitational capture would instead behave like a decaying thermal system. The paradox becomes sharper when scale is introduced. Large stellar black holes would evaporate so slowly that the process would remain effectively invisible across the entire current age of the universe. Yet current models indicate that the mechanism never fully stops, meaning the disappearance could still occur given enough time. This creates an unusual observational problem. The mass loss signature is predicted mathematically, but no direct evaporation event from a stellar black hole has ever been conclusively detected. The system therefore exists in a state where theory strongly implies a physical process that observational astronomy cannot yet confirm. The contradiction deepens because the radiation itself appears random. If particles escaping the black hole contain no usable information about what originally fell inside, then the evaporation process may permanently erase physical information from the universe. That outcome conflicts with fundamental assumptions in quantum mechanics, where information is generally expected to remain preserved. One possible explanation suggests that the information is not truly destroyed, but encoded in subtle correlations within the outgoing radiation. Under this interpretation, the apparent randomness may hide an underlying structure too weak or too complex to currently measure. The paradox remains open because no complete mechanism has shown exactly how such encoding would operate. Another interpretation proposes that the event horizon itself may not behave as a perfectly smooth boundary. Quantum effects near the horizon could alter space-time behavior in ways that standard gravitational models do not fully capture. This possibility shifts the contradiction away from the radiation and toward the structure of the black hole itself. The problem is that neither explanation fully resolves the conflict between gravity and quantum theory. General relativity treats the black hole as a geometric space-time system, while quantum mechanics treats the radiation as probabilistic particle behavior. The evaporation process appears to require both frameworks simultaneously, yet the two models do not combine cleanly under extreme conditions. The expected thermal behavior introduces another cognitive contrast. Black holes are often understood as the cold endpoints of collapsed stars, systems defined by permanence and irreversible capture. Evaporation instead implies that they behave more like unstable thermodynamic objects, slowly dissipating energy into surrounding space. This shift changes the meaning of the event horizon. Rather than functioning as a perfect one-way boundary, it may represent a region where quantum uncertainty continuously interacts with gravitational confinement. The horizon would then become an active physical interface instead of a passive edge in space-time. The timeline of the process expands the uncertainty even further. As evaporation continues, the black hole becomes smaller, and smaller black holes are predicted to radiate faster. The final stages may therefore accelerate dramatically, transforming an almost frozen system into an unstable burst of energy near the end of its existence. Current models become increasingly unreliable near this final stage. The black hole would eventually approach scales where quantum gravity effects may dominate, but no complete theory currently describes physics under those conditions. The causal chain therefore reaches a boundary where the evaporation process can no longer be modeled with confidence. The observable consequences remain uncertain because the end state itself is unclear. Some models suggest complete disappearance, while others imply the possible survival of an extremely small remnant retaining hidden information. The paradox persists because both outcomes introduce unresolved physical problems. If the black hole fully disappears, information preservation becomes difficult to explain. If a remnant survives indefinitely, current theories struggle to explain how an object containing enormous informational complexity could remain compressed into an extremely small physical state. The contradiction therefore survives regardless of which conclusion is chosen. Another contrast emerges from the relationship between entropy and gravity. Black holes are predicted to contain enormous entropy, implying vast hidden internal complexity despite appearing externally simple. Evaporation slowly releases energy outward, yet current physics cannot clearly describe how that hidden complexity evolves during the process. The radiation leakage process also challenges the traditional idea of cosmic permanence. Stellar black holes are often treated as among the longest-lasting objects in the universe, surviving long after stars and galaxies change form. Evaporation suggests that even these extreme gravitational systems may only be temporary structures on sufficiently large timescales. This introduces a broader observational uncertainty. The universe today may simply be too young for stellar black hole evaporation to become directly visible. The absence of clear evidence may therefore reflect a timescale limitation rather than the absence of the process itself. The physical system then reaches an unusual state where theory predicts a phenomenon that observation cannot yet fully test. The mechanism appears mathematically consistent in some contexts, but the deeper consequences create contradictions that modern physics still cannot reconcile. The evaporation process remains suspended between predictive success and conceptual incompleteness. The paradox survives because every explanatory path appears to expose another unresolved boundary. If radiation escapes, information preservation becomes uncertain. If information survives, the mechanism remains hidden. If gravity and quantum behavior both contribute, their combined framework remains incomplete. What initially appears to be a slow mass loss process therefore expands into a deeper conflict about the structure of physical law itself. A black hole may not simply disappear over time. It may expose a region where current models of space-time, entropy, and quantum behavior stop aligning in a fully coherent way. The instability grows more severe as the black hole loses mass. Smaller black holes are predicted to emit radiation more intensely, causing the evaporation rate to accelerate instead of slow down. A system initially defined by gravitational permanence may therefore evolve toward increasing instability near its final stages. This creates a difficult propagation problem across time. A nearly undetectable leakage process operating over trillions upon trillions of years could eventually dominate the entire physical behavior of the object. The anomaly is not explosive at first, but cumulative, which makes its long-term consequences difficult to isolate observationally. The observable signal remains extraordinarily weak for stellar black holes. Any radiation escaping through the evaporation process would be overwhelmed by surrounding cosmic background energy, accretion activity, or other astrophysical emissions. The predicted signature therefore exists beneath multiple layers of observational noise. That limitation creates an unusual dependency in the models themselves. The mechanism appears theoretically clear at timescales that cannot currently be observed directly. The farther the projection extends into the future, the more central the evaporation process becomes, yet the less empirical confirmation remains available. The contradiction also propagates into thermodynamics. Black holes are expected to possess temperature through their radiation behavior, but the relationship behaves inversely compared to ordinary systems. As the black hole loses mass, its effective temperature rises rather than falls, introducing a thermal instability that grows stronger as the object shrinks. This reversal produces a visible conceptual break in intuition. The colder and larger the black hole becomes, the more stable it appears. Yet the closer it approaches disappearance, the more violently the leakage process may intensify. Current equations remain relatively stable while the black hole is large. The problem emerges when the shrinking system approaches extremely small scales, where space-time curvature becomes increasingly extreme. At that boundary, general relativity and quantum behavior begin generating incompatible descriptions of the same physical region. The event horizon itself may no longer behave as a clean geometric surface. Under those conditions, quantum fluctuations could distort the structure of the boundary faster than classical gravitational models can describe. The evaporation mechanism therefore threatens the stability of the horizon concept that initially defined the black hole. The observational consequence is subtle but severe. If the horizon becomes physically uncertain, then the distinction between trapped information and escaping radiation also becomes uncertain. The paradox spreads from particle behavior into the geometry of spacetime itself. One interpretation suggests that information may gradually leak outward during the evaporation process in highly scrambled form. Another possibility is that the information remains inaccessible until the final stages of decay. Both interpretations preserve parts of existing theory while failing to fully explain the observable consequences. Neither explanation cleanly resolves the propagation problem. If information escapes continuously, current models cannot fully describe the transfer mechanism. If it remains trapped until the end, the final evaporation stage may require an information release process too extreme for known physics to support. The instability then expands beyond the black hole alone. Evaporation implies that even the most gravitationally dominant stellar remnants may eventually transition into radiation-dominated systems. Over sufficient timescales, the balance between matter confinement and energy release could reverse completely. The observable universe today offers no direct example of this final transition. Stellar black holes remain far too massive and too young for rapid evaporation signatures to emerge naturally within current observational windows. The absence of visible decay therefore does not eliminate the mechanism, but it prevents direct verification. That observational silence becomes part of the paradox itself. The process is theoretically unavoidable in many models, yet its strongest effects occur at scales of time that modern astronomy cannot physically witness. The mechanism remains suspended between mathematical necessity and empirical inaccessibility. A smaller black hole would radiate more intensely than a larger one. The system becomes brighter as it approaches destruction, even while losing the mass that originally defined its gravitational power. This creates another structural contrast. Gravity initially dominates the system completely, compressing matter beyond escape. Yet near the end of evaporation, radiation behavior may become the dominant physical process instead. The final stages remain especially unstable because current models depend on equations that assume smooth spacetime continuity. At extremely small scales, that assumption may fail entirely. The evaporation process therefore approaches a region where the underlying mathematical structure of gravity itself may become incomplete. Some calculations predict an explosive final release of energy. Others suggest the evaporation could stall before complete disappearance, leaving behind a microscopic remnant with unresolved internal structure. Both outcomes preserve different parts of known physics while generating new unresolved constraints. If a remnant survives, the system may contain more hidden information than its remaining size appears physically capable of storing. If no remnant survives, the information loss paradox intensifies because the entire gravitational system disappears completely. The contradiction sharpens regardless of which outcome is selected. The radiation leakage process therefore behaves less like a simple decay mechanism and more like a boundary test for modern physics. Each stage of mass loss appears to transfer the paradox into a deeper layer of the system, from thermodynamics to space-time geometry to quantum information itself. The longer the timeline extends, the more unstable the explanatory framework becomes. What begins as a slow mass loss signature eventually reaches conditions where the evaporation process can no longer be separated cleanly from the unresolved structure of physical law. Current physics can describe large portions of the evaporation process mathematically, but the explanation begins to fracture near the exact point where the black hole approaches disappearance. General relativity continues treating the system as curved spacetime, while quantum mechanics continues treating it as probabilistic radiation behavior. The two frameworks remain individually successful while failing to fully align under the same conditions. The black hole therefore changes status within modern physics. It is no longer only a gravitational object or a collapsed stellar remnant. Through evaporation, it becomes a boundary system where information, entropy, radiation, and space-time geometry can no longer be separated cleanly without contradiction. One constraint now appears unavoidable. If evaporation is physically real, then the event horizon cannot behave as a perfectly sealed boundary across all scales and all times. Some form of interaction between gravitational confinement and quantum behavior must persist, even though the mechanism responsible remains unresolved. The observable implication is cold but direct. A stellar black hole may spend most of its existence appearing stable, dark, and permanent, while already losing mass through a process too weak to detect clearly. The system could be decaying long before observation becomes capable of confirming it. That leaves the paradox open at its deepest level. The evaporation process appears consistent enough to predict long-term mass loss, yet incomplete enough to prevent a fully coherent explanation of what ultimately happens to the information trapped inside the black hole. Current models can follow the decay forward, but not all the way to a final physically stable conclusion.